So I found it's actually UHCC at 2014, the talks by Javier Gonzalez, where he actually used universality to extract what would be the effect on the scintillators that have more muons. And actually, it's complex because you have to take into account the difference between the experiment and so on. And at the end, he found something like 25%. So it actually does work. It's the same at this time. This 80% excess in Auger compared to QJ23 could explain, because we are 80%. So this could explain this 27%. So okay, and but about the model. So why? So I showed this morning. Maybe we have we found the solution. But let's discuss anyway. I think there was two really important points. Or maybe sorry. Okay, yeah. I think there is two crucial points in my presentation this morning. Was the cross section, which changed X max. So this is important. Yeah. So just I put it here that in fact the data, so these are data, accelerator data, proton carbon and pion carbon and point on simulation.
Yeah. I'm sorry, let me interrupt you. I think in restricted time, we should not try to discuss now everything. We have just time to discuss cross-section.
No, if you want. I have only 2 slides.
And since it's really an important point, yep. We can really clarify this point. Then we slowly, if time permits, we can move further.
Yeah. I will not. I don't have a presentation like Antenella. It's just 2 slides, one with cross-section and one with particle ratios. So we can stay on this one or go to the other. Yeah. Yeah. Okay. So what I wanted to show here and to start the discussion is that, so in EPOS LHC, I could indeed reduce quite a lot the cross-section, but EPOS LHC was the highest. Yeah. So if you go down, actually, you are very close to QGJ24 at the highest energy, not at the lowest energy. And if you, on the left, you have actually data from accelerator, and you see that I am, with this new version, better than the previous version, in fact. And Sibyl and QGJ are actually quite good to describe this data. But then anyway, you get some large, at the extrapolation, you get large errors. Even is also for proton, you get now very, very consistent picture. So there is some uncertainties here. And okay, now, Sergey, I guess you have to say.
The plot on the bottom right, when you say AP, is it anti-proton or?
Proton, anti-proton, okay. Yeah. It's because it's mixed, the data point. Okay.
Yeah. I would really go step by step. And what questions do I raise? Question 1. Is proton-proton cross-section sufficiently precisely measured now at the LHC? Essentially, we should use only Atlas, alpha, and total. Well, other measurements, they are much more inferior. Total and Atlas, so both based on Roman. I think one should really forget the rest. So first question, if it's now precise enough, taking the difference between 2 experiments as the characteristic uncertain. And second question, is Glauber good enough? Or there are alternatives, or there is a need to improve on this point? And here I want to make one correction. For the moment, let us postpone discussion of Gribov's inelastic screening and diffraction. This will be second point. So for the moment, let's forget about diffraction, forget about inelastic screening. 2 points. Are things measured well enough at LHC? Is Glauber good enough? Or there are doubts about its validity, and one should do something better or different?
On the precision at the LHC, I think exactly these 2 measurements, alpha and totem, they're not exactly the same results. And they're inconsistent.
2.6% difference for inelastic.
So that's very unfortunate, right? Because it limits the precision that you.
Yes, but I would argue that it's a good precision, because once we go to proton nucleus,
it's irrelevant. Yeah.
you know, it's only a small periphery region which counts, but the main cross section is area. Again, I discussed in the Glauber picture or something like this. We have just a shadow. So everyone is open to comment on the accuracy. And second question is Glauber. To my knowledge, Glauber model has been tested enormously over the past 6 decades, not only in elastic and totem, but also differential distributions, differential scale. And I'm not aware of anything competitive to this approach.
Again, when you measure, say it has been measured over the last 6 decades, even to what level of precision? Not that I would doubt Glauber, but I mean the question is how precisely do we know? Do we need to know?
So, Tanguy, do you allow me to share something here? Okay, because what Sergey actually says is an interesting question, and people ask this sometimes. So this is a Glauber out of the box from actually really the original Glauber and Mathieu publication with proton and carbon data where we have very good data, not too high energy, but and now I show you with screening corrections. Sadly, I have not. So just remember this curve is a little bit departing here. Yeah, and the story is what I want to show you is that Glauber works beautifully, but not completely out of the box. At least sometimes people tend to forget the screening corrections, and Sergey mentioned this.
But I wanted to postpone it to the second step.
No, but it is actually important if we start to discuss the details. And if you do the screening correction, and that's not tuned to match the data, it's actually what we believe the screening correction should be like. And then it looks much better. So we have no indication that it's not going to work, at least in the where we have data. It's actually working beautifully. And so my claim is actually, Chloe, what you showed, the differences are too big. So we in principle should know really to the spot where we should be. If we agree on the proton-proton cross-section, if we agree on the pion-proton, there's not much room left after doing the Glauber calculation. And I'm very much supporting what Sergey says, one should use Glauber. So
you're saying between when I showed the projectile's nucleus against the nitrogen and the difference?
That is then just a higher incarnation of the same thing. Yeah.
Okay.
Well, maybe some models you had proton cross section, some proton nitrogen. This would have explained partly.
I had simply the proton air Auger point, but everything else was proton nitrogen or proton oxygen.
That was also
So it only explains the difference between the points not overlapping with the curves. That's about it. But all the curves within themselves are the same simulation.
But we are talking about 10%. Huh? So how certain or uncertain are these screening correction? Where do they come from? And
exactly, Tanguy. This is the second point. And let me just say a few words. Coming to screening corrections, one thing I should keep in mind right away, this is closely related to inelastic diffraction. And to my knowledge, the only model approach to explain this, proton is not elementary object. Proton is represented by different states. In an interaction with media, probabilities. And unless you assume that there are such different states, you don't have diffraction at all, and diffraction is measured. And this way we get a handle on an elastic correction, because we have measurements of diffraction. If one has more or less reasonable model, having described one, I mean diffraction, one gets automatically the answer what Ralph showed for the inelastic screening correction. And Tanguy, one thing which was missing in your talk, you didn't stress it, that your 10% effect doesn't count from the difference between totem and atom. It does come exactly from the inelastic screen.
Yes, I tried to say it, but maybe it was not clear. Yes, yeah. But is Globber implemented in QGIS completely, or is your own way, like in EPOS? Or because look, here you clearly have a big difference between Sibyl QGIS, between Sibyl and QGIS on your. I mean, we have the same proton-proton cross-section as this energy, yeah? So clearly the trend is different. So how do you explain it in your case?
That's really a good question, because the treatment of inelastic corrections is model dependent. One can do a continuum of such different states. One can do what I do with multipomeron diagram. It's the same physics, but described by a different apparatus.
So can we claim a better than 10% precision because of these uncertainties and at this level? I mean, on the elastic and diffraction.
You could anchor it on the proton carbon, for example.
Yeah, but no, look, we are supposed to be anchored on this proton carbon, and
Yeah,
you see,
and if you aren't on the line, you do something wrong because it's data.
yeah, but QGIS, I mean, both you can say it's not the same trend, but it's within the uncertainty. You can argue probably, yeah. I guess Sergei cannot do better than that, otherwise we would do it. Maybe QGIS 2.3 is different. I don't know. Because at the end of the day, if you look at the proton air cross-section, we have a big difference at low energy between EPOS and QGIS, and then at high energy, because you have a different trend, you converge. And actually all the models converge now at highest energy. It's more in the middle that you have differences. So, and I have a question actually. Should we trust this OJ point that actually you can use it to I am, but it's for the sake of the discussion. It's for the discussion. It's for the discussion. I'm fired. So yeah, can we use this point in the tune? Because this point actually also depends on the model, because there is the inelastic correction, diffractive correction on this point where we use the model. So it's like a loop.
So Tanguy, I think this is, of course, on air as a target. And on air as a target is much more complicated. You should show where we really have measurements, and that's carbon, where it's done with a proper lab beam. And there we have the results, and there we should agree. And if we go to air, it's all indirect measurements from cosmic rays and whatsoever. It's much more complicated, and we will never be sure to be so accurate there. But here, in principle, we should know.
So we don't really trust the OJ point.
Well,
Is that your answer? No,
we
because I'm
don't
interested
really
as well.
trust to the extent that, I wouldn't,
You
wouldn't
wouldn't
bet my
constrain the
hands on it.
tune
No.
around this. Okay.
I would go to the lab measurement where you have everything under control, because for air as a target, it's much more complicated.
Therefore, our highest are the NA61 datasets.
No, it's actually Selex is the highest. So there are measurements, I talk about the total cross section or the inelastic one. So these are different measurements.
From this measurement, we could say that maybe QGIS underestimate the very low energy. So the slope is not correct here. Maybe. Yeah, but it's EPOS. It's an old one. Actually, I'm surprised that it was so bad. Yeah, I didn't remember because it's outdated. Yeah. No, but I never said it.
Yeah. So I would really address Tanguy's question from a different point. I wouldn't argue that my particular mouse is the best mouse in the world, but in general, you have an approach. In general, the higher diffraction you have, the stronger elastic screening effect you have. What I want to stress that to have a strong reduction of the cross-section on air, like proton air, you have to have high diffraction in proton-proton. How much high may depend on the particular thing. What I want to stress, there is a handle on the set. And this handle are measurements of diffraction in proton-proton.
Sergey, don't we see in your part that you don't really try to fit the proton-proton cross-section at the lowest energies? Isn't that the case? I mean, that so it's not really from the inelastic screening or something else. It's because you don't probably have a region or whatever.
Exactly.
Yeah.
I wanted to say that because if you look at proton-proton, there you need returns.
Should we try to go to the next point or? Yeah, I prepared full plots that was not ever done before. So yeah, yeah, I'm going there. So I did a little game which I found interesting. So I took this Alice data, which depends uniquely on the centrality, I mean, the number of particles at mid-rapidity, okay? So this is a universal measurement you can do in any condition. So I took proton and pion air interaction as, at all energies for 100 GeV to 10 to 20 electron, yeah? So I just run everything, and then I just look for each event at the multiplicity, and I put it on this slide, on this plot. So here you have actually a mixture of all the energy from the lowest to the highest energy for all the models for pion and proton. So the two lines are the same color as proton air and pion air. And this is what you get. So I find it quite interesting. So for QGZ as, and it's of course the ratio of kaons to the pion. So it's this data, it's Alice type of analysis. And it's only at mid-rapidity. So this can be different forward. Yeah, be careful with that. And yeah, and the models give you very different results. So for QGZ, it's flat, as I think it's expected, yeah, because you have just string fragmentation and no dependence on anything. And so it's what you basically get, except for the lambdas. Actually, you get a very nice description. I don't know why. And for proton, it's overestimating, but also other models do. Sybil has some dependence on the energy, and this I don't know why. And it has a lot of protons on this picture. I also don't know why. And for EPOS, it's actually increasing. It's the core-corner effect. And here it's really overestimating. And I know why. I mean, no, yes, I know why. And what is missing there in this picture is this hadronic cascade. So what happened after the interaction. So in lead-lead, for example, you will overestimate the proton, and then you have this hadron-hadron interaction, and the protons will disappear. So they annihilate or they transform into neutrons or different particles. So the yield looks different. So it may actually be the hint that we need that also for air showers. So I will work on this actually. So yeah, lambdas, oxide, QGH cannot do it. And that's thing. What was also interesting is to look at the pi zero, so pi zero fraction, and you see that actually QGH and EPOS give exactly 0.5. So we actually have 1 to 1 to 1 in terms of pions here, but not Sybil. But I was really surprised. And then I also did different, which is what is in present relevant for the muon productions, which is not just the pi zero to charge pion ratio. It's here it's for simplicity, I didn't have time, so it's actually everything minus pi zero divided by pi zero. So it's the inverse of what you want for the muon production, but it doesn't matter. So this is the higher here, the more muons you will produce, and you see that actually you have no multiplicity dependence in QGZ. This is expected. You have an increase in EPOS. This is the core-corona effect, and in Sybil you have something, yeah, in between. Yeah.
The page back. So those plots are very interesting. And but I think if you say now this is a complicated cancellation effect or 5 different things, I would say we just haven't got it right. Not a single of the models, because not a single one, because it looks like a very simple relation that we have to produce. And it's very hard for me to imagine that this is like produced by 5 effects that compensate each other and have to be tuned to the detail, that it's really working for the protons, for the kaons, and the lambdas in different ways.
So you will see that
I think actually there is something more fundamental here, and we haven't got it.
So you will
It's
see
not in the models. Yeah,
you will see in Klaus talks tomorrow where it really goes into the details, and actually it does. And if you look, because these are standard particles, but if you look at more like exotic, like resonances and rows, it's a completely different pictures that you explain very well with the same corona plus hadronic cascade.
And
So
why don't you have it? Because you don't have corona in here?
No, here I don't have the hadronic cascade. That's the thing I have to add. Yeah. So I don't know. I mean, I will, we will see if it's enough.
But you see my argument that that's, for me, the functional relation looks fairly straightforward and simple.
Mhm.
And the models look much more complicated because they just haven't got the physics. Yeah.
No,
So
I mean,
this is what I would say. Yeah.
yeah, we can talk about later yesterday after Klaus talk, because
Yeah,
I can explain if you want, but it's not the point now, I think.
No, yeah.
He will explain it, hopefully. And yeah, no, but it's interesting. For example, why is there any energy dependence in Sibyl on this particle production? Why you have just strings in principle, like QGH. So is there a reason for that?
Or you mean why there is a dependence on the multiplicity? I don't know, really. I mean,
Felix?
we will have to look, but that's yeah, no idea. Maybe Felix knows. Yeah, but
No.
I only wanted to say if you come with reasons for one plot or the other and whatever, and in the end different mechanisms produce the same curve, this is just unlikely. I would just go to the simple explanation that there's something else behind it.
But it's really surprising that, I mean, the proton to pion is that bad, while the lambda to pion and even cascade to pion is well, but
Yeah, so
strange. That is very strange. I mean,
if you look at the fixed energy, so if you look at LHC, actually, QGH or will reproduce that very well. So I think there is a contamination or something from another energy. So
no, but it's function multiplicity. Do I misunderstand?
yeah. So here, the multiplicity, I mean, the energy would go into the multiplicity, because the higher the energy, the higher the multiplicity. So basically here you see that the proton ratio will decrease in with the energy in Sibyl, while it will increase in EPOS.
Yeah.
So that's strange.
But if you look at the fixed, I have it that way. Look at this. Yeah, here. So this is a lambdas. You see, as a function of multiplicity, it's completely different picture. The lambda, I think I have it here. Yeah. It's flat for Sibyl. Okay, it's a bad example. It's also
Let me say this. I would again prefer to make it in a constructive way, not really discussing particular models, but general picture. If we have basic standard picture, standard UCG, standard region description, we have things flat. In order not to have it flat, we need collective effect. This can be done. This was addressed in particular by Peter Scans. One can do collective effects differently. Peter Scans does this color reconnection.
Mhm.
You do thermodynamics. You get this by putting extra to the basic picture.
Yeah.
And the problem for me is this extra is less fundamental compared to the basic picture. You are more dependent on particular approaches, particular recipes. So here we really come to a very important question. How important are collective effects for extensive showers? Do they impact exotic things like this dependence, which is very important for PCA here, because they really want to describe background for physics searches. How important is this for showers where we have average collision? For me, there are only two answers. Answer one, it is relatively unimportant. Then we can more or less predict things with the basic approach. Alternative, it is very important. In such a case, I would consider that we can predict nearly nothing, because we really rely on particular approaches up to the taste of the authors and so on. So I would really put it like this.
So to answer that, agree. And then, but then we have data, and the data tells us it's there, and the air shower data tells us we have a problem. And I can, and with my version now, I can do the link, and then I agree with you that it increases a lot uncertainty. So can we at the end then predict this in a way that we can rely on it? That's a good question. What we can do is cross-check with hybrid measurement, multi-hybrid things. If we get a model which is able to reproduce all this data consistently, I think it would be a good sign that it's not so crazy. Yeah?
And the problem is, as I said, we don't have a fundamental approach for this. And to describe, well, for me, it is never enough. If you have an approach, you are able to predict. To describe is a very different thing.
Yeah, but I think the corona picture has a predictive power. I mean, that's because indeed it was done before any data. I know actually there was data, but nobody was interpreting like that at this time. But the data were not, I mean, people were not believing in that. And then it appears to be actually a correct description of the data coming later. So this is a prediction. So I agree it's complex, but it's not that, I mean, as Klaus will explain, but this, like this hadronic scattering, there is no, there is no parameters. I mean, it's.
Sorry, I'm not going to criticize you. I'm not going to disagree with you, but just a simple thing. If you consider old QGIS chat model, I was always unhappy with it because it missed this. But even you compared it to the first LHC data for many observables, it was quite good.
Yeah, but for very basic,
for me, this is really a bad argument. If something which is obviously not correct still works reasonably with the data, I wouldn't buy it as an argument for the validity of the approach.
You are talking about few distribution. I mean, the corona, I think, is based on thousands of distribution. It's not like two very simple example. So, okay, no, but I agree that this increases the uncertainty because how to extrapolate and so on. But I think that the beauty of the corona thing is that you don't, at extrapolation, you see it here. You don't have, it should be universal somehow. So there is no energy dependence. There is not such a thing. So for me, it gives me some confidence that actually it's a good test for also the high energy extrapolation. We'll see. Okay, let's try, and it's good to have different approaches.
Let's come back to the basics. Either collective effects make a strong imprint, or we may discuss how well can one control them.
Yeah. So I think it has a large impact, and yeah. Whether it's under control, this is more open to discussion, of course.
Yeah, I think we because I was asked, we should not start too late with the next session. So we have now, I mean, it was a very interesting discussion. I would have liked to continue, but I mean, also we have some other constraints later today. It was really useful, I thought. I mean, all the different topics. And even though if we could not come to a final conclusion, but I think the direction was expressed well. And yeah. So we will now have, thanks for all the conveners. I mean, to all the conveners, that was really very helpful.